Okay, let's take a look at an exercise involving a special collision type, a perfectly inelastic collision. So one in which the objects stick together after the collision. So inelastic. So not elastic at all. They stick together after the collision. So we have a linebacker tackling a halfback, and the linebacker was slipping. I guess we can infer from this that it's slipping without any friction at some velocity north, and the halfback is sliding without friction, some velocity east. And we want to know what is the velocity of the two players, which are stuck together because one tackles the other. So they're stuck together, and what is the velocity of the combined linebacker and halfback immediately after the collision? So we have a collision, right? So this suggests that we have some conservation of momentum going on, because we can use conservation of momentum during any collision. And our general process for solving conservation of momentum problems is to draw before and after pictures, because that's when we have momentum conserved, before the collision and immediately thereafter. So let's go ahead and establish a coordinate system which we'll use for both the before and the after. I'll call this is positive x will be the eastward direction, positive y would be my north direction here, and say north is positive y, and we need before and after pictures. So we have something before, and then we'll have something after, and I use the same coordinate system for both. So before, there's one object here and another object here, and then after, they're a combined object like this, right? And something like that. And this one was moving eastward, right? 7.2 meters per second east. So this one was moving this way, 7.2 meters per second. And another one was moving north at 8.8 meters per second, something like this. So just extracting all the given information in this figure, kind of like we did with free body diagrams. But these aren't forces, this is a velocity, right? And also we know something about the masses as well. It was the linebacker that was 110 kilograms, and that one that's going north, so this is the 110 kilograms. And then we have the other one was 85 kilograms, like this. And then after, since they're stuck together, they're going to have a combined mass here that's going to be the 110 plus 85. So this is going to be 195 kilograms. And it's going to be moving at some velocity that's probably, if this one was moving to the right and this one was moving upwards, it's probably going to be up and to the right. So something like this, yes? So this would be the final velocity. And that's going to be, we can define, since it asks us to find both the magnitude and direction, we can give this direction in terms of some angle off the horizontal, like in standard position, call this theta. So I can have a magnitude of the velocity at an angle theta. Okay, so there's two unknowns here, right? There's actually, we need the magnitude of the velocity as well as the angle, right? So there's two unknowns, so we really need two equations here. Now, conservation of momentum might at first sound like it only is one equation, right? I just have initial momentum equals final momentum. Only one equals sign. But momentum is conserved in every direction. So just like we did back in the kinematic equations, we only look at one direction at a time. We looked at just in the x direction, just in the y direction, right? Back in projectile motion. We do the same thing with momentum. If momentum is conserved, then it's conserved in every direction. Well, in most cases, unless you have some external force in one direction. So So in this case, momentum would be conserved both in the x and the y directions, right? And so we would have here, if the initial momentum is equal to the final momentum, then this would mean that the initial momentum in the x is equal to the final momentum in the x, and the initial momentum in the y direction is equal to the final momentum in the y direction. Both of these are true. This is getting to be a really slappy P. Okay, so both of these are true. So I can then come up with two equations, right? One for momentum being conserved in the x direction, one for momentum being conserved in the y direction. And if I have two equations, I can find for two unknowns. Namely, these two unknowns are the magnitude of velocity and the angle of it as well, right? So let's just write that out then. I have here the x. I'll start out in the x direction. Oops. The x momentum, looking at this, this is just in the y direction, right? So that one will play no role in the x component momentum. It'll be only this one here, right? So just the 85 kilograms at 7.2 meters per second. And so we have the initial momentum in the x direction. This is equal to 85 kilograms times, what was it, 7.2 meters per second. And that's our initial momentum in the x direction, which comes out to 612 kilogram meters per second. No special units for momentum, just kilogram meters per second. Now, the final momentum in the x direction, we need to write that out as well. So P final in the x, and this is what contains a lot of our unknowns, right? But I do know the mass, it's 195 kilograms. And the x component, if I leave this as magnitude of v and some angle theta, then the x component of the velocity would be v cosine theta. And the y component would be v sine theta, right? Given that theta is in standard position. And so I'll just write that into the equation. So the final momentum in the x direction, this is going to be 195 kilograms times v cosine theta meters per second, right? So this gives us that we have 612 is equal to 195 v cosine theta. Or I could, this is Vx, right? If you wanted to write it out that way, I'll leave it as v cosine theta. Okay, two unknowns in there. We just need one more equation, and we can get this equation by solving in the y direction, right? So I'll just highlight. Here's our first equation. To get the second equation, we have the initial momentum in the y direction is equal to, it's very convenient that these are, one was just heading east and one was just heading north, but if they were headed off at some angles, the first step would have been to, let's say this one were going that way and this one were going this way or something, then we would have broken them into components first, right? And then we would have, we would have had a little bit more to add together, but this was just set up very, very simply for us. So the y component momentum is 110 times 8.8. Right, so the initial momentum in the y direction is 110 kilograms times 8.8 meters per second, and this comes out to 968 kilogram meters per second. And then the final momentum in the y direction, this is equal to the total mass, which was 195. And the y component of velocity was v sine theta, right? And so then setting the initial equal to the final, because momentum is conserved in the y direction as well, then we have 968 is equal to 195 v sine theta. Right, so this is our second equation we can use to solve this. So with these two equations, there's a few ways that we can go about it here. You can solve it any way that you really want. Substitution, elimination. We can also take and I can actually divide one equation by another, and it works out to be exactly the same as just substituting. I can take this equation here, and then I can divide by the other equation, the one that we had. This is another way of combining them. Divide by this one. And what we end up with is, let me divide here by 612 is equal to 195 v cosine theta. This is exactly the same as just substituting, like solving. This is exactly the same as just solving for maybe v here, and then just plugging in to the equation. But this is a nice little shortcut, as long as I'm sure that one of the equations isn't equal to 0, which I'm sure in this case. And what happens when we do this is that the 195's cancel and the v's cancel, and we just have, and we just have the sine theta divided by the cosine theta, which is tangent theta. And so what we end up with is that 968 over 612 is equal to tangent of theta. And so then the angle theta is the arctan of this 968 over 612. And so theta comes out to 57.7 degrees. So that's our angle there. And then we can take this and we can plug it back into either one of these. So if I have theta here, I'll just plug it back into here. Either one. And we can say that 612 is equal to 195 times v, I can't remember, was that sine or cosine? Cosine. 57.7. And solving for v, we get the magnitude of the velocity is 5.87 meters per second. Maybe I should call this v final. And this is magnitude. I didn't put the vector notation, but I'll emphasize the fact that it's magnitude here. Right, so we can say here the final velocity, therefore v final is equal to 5.87 meters per second at 57.7 degrees. Alternatively, if you wanted to, just to kind of show an alternative way to do the math, which could, depending on what we're given, this could actually be quite a shortcut. Let's say here, we could say, the magnitude of the final momentum has to be equal to the magnitude of the initial momentum, right? Momentum is conserved, they have the same magnitude, yes? The momentum itself is the same, right? This is the final equals the initial, but including both directions here, right? So let me just look at the magnitude. And so the magnitude of the final is the magnitude of the initial, and the magnitude of the initial momentum would be, well, I found the y component of the momentum was this 968, right? This was the y component of the initial momentum, and this was the x component of the initial momentum. So I could put both of these in here. So I could say this is going to be the square root of 612 squared plus 968 squared. So that's the magnitude of the final momentum. This comes out to 1145.24 kilogram meters per second. But this is equal to the total mass times the magnitude of the final velocity, right? And so, given the fact that we know the total mass was that 195 kilograms, then we can just divide both sides by 195. I can get the magnitude of the final velocity is going to be 1145.24 divided by 195. And this gave us 5.87 meters per second, which is exactly the same as what we found previously. So once I find this magnitude of the final velocity, I could then plug into either of these equations here to find out what theta is. So a couple of ways to go about it. One way I found theta first, then found the velocity. Another way I found the velocity first, then found theta. But it's worth noting this is the magnitudes are the same, and so if you know the final mass, you can get the magnitude of the final velocity pretty easily there. Especially like, let's say we were just given the magnitudes of these momentums, then this would have been a much faster way to go about it.